Okay, so here are the notes for day 20. This is the second day on section 4.1, and again, we're working with antiderivatives and indefinite integrals. These directions were copied straight out of the book, so when you see a homework problem similar to number 51, don't be intimidated by all the instructions. Basically what this says is that here's a slope field. It's a visual way of representing this differential equation. So instead of saying y equals something, we have a rate equals something, the change in y over the change in x. And these blue lines represent slopes at different locations in the plot. To solve for y is going to be the function that creates a straight line, a continuous line that has these slopes. So the process is sketch two approximate solutions on the slope field, one of which passed through the indicated point, and then use integration to find the particular solution to the differential equation and use a graphing calculator to graph the solution. So to tackle part A, sketch two approximate solutions of the differential equation. All you need to do is come up with a line that travels through these slopes, okay? The second answer needs to go to the given point. So the point is at 4, 2. So I'm going to draw something that looks like that, okay? The reason why I think that these are correct is because if I look at the equation here, if I plug 0 into this statement here, when x is 0, my slope is going to be -1. So when x is 0, in other words, along the y-axis, all these lines have a slope of -1. So the tangent line at my answer needs to have a slope of -1. So this blue curve looks like it has a slope of -1, and so does this blue curve, I guess, at that point there. If I were to plug in 2, x is 2, 2 times a half is 1, 1 minus 1 is 0. At x equals 2, I should get a slope of 0, and a slope of 0 is a horizontal tangent. So I should have a minimum at x equals 2. I didn't exactly draw that too well, but if you have a horizontal tangent, that's when your slope is equal to 0. So to get part B, use integration to find a particular solution. Bring the dx to the other side. Undo the derivatives by taking the antiderivative of both sides. Remember that the antiderivative of a number is x, and then the antiderivative will always have a constant. Since we were told the function needs to go through the point 4, 2, I can plug in 4 for x and 2 for y and figure out what that constant is. And there's the function that travels through that point. And again, I could have drawn a little better, but there should be a minimum at x equals 2. Okay, so that's how you tackle slope field questions. The second one is similar to that. You are given a differential equation, and you're asked to find the equation for y that goes through that point. So I've hidden the answer with a nice little prairie thing here with a sun. Go ahead, see if you can answer this. Pause the video, come up with the answer, and then check the answer when I move the pretty picture out of the way. Okay, moving the picture out of the way. Antiderivative of both sides, we'll move the dx to the other side. Antiderivative, you get this statement. Plug in the 0.26, you wind up with c equals 2. It's a cubic. Looks like that. Notice if the y-intercept of this cubic is 2, so the heavy line, the one that's the specific solution, not only goes through 2, 6, but has a y-intercept of 2. So a new topic here is going to be position, velocity, and acceleration. For a given position function, what is the velocity function? If you know a position, and if you take the derivative, you're turning that position into a rate. So the first derivative of a position function is a rate or a velocity function. What's important to know here is that velocity is not the same thing as speed, and I'll discuss that in a few seconds. Also, position is not the same thing as distance. Where you're at is not the same thing as how far you've traveled. Continuing the derivative, if I take the second derivative of a position function, that's the same thing as the first derivative of a velocity function. How much a velocity is changing is known as acceleration, okay? If you start at the other end, if you're given an acceleration, what is the velocity function? We need to undo derivatives. So if I start at acceleration and want to go backwards, I need to undo a derivative, which is an antiderivative. So if I take the antiderivative of an acceleration, I get a velocity. And if I take the antiderivative of velocity, I get a position. And don't forget about your plus c's. These are just general ideas. When you go to use actual functions, you will have to have plus c's. Okay, so what is speed? Speed is the thing that you look at on your dashboard when you're driving. Whether you drive north, south, east, or west, your speed is always going to be positive. your velocity may not be positive because you might say north is positive and south is negative. So speed is the absolute value of velocity. In order to get the total distance that you've traveled, you don't want to use position, because if you go back and forth between places, your positive and negative positions will cancel each other out. But total distance will be the sum or the antiderivative of your speeds. So it's the antiderivative of a velocity function. We'll be doing more with this later, but you'll get a number of examples on how to deal with total distance and speed, okay? So, third example, solve the differential equation. You're given the second derivative, and solving means you need to find the f function, or y equals. So you need to undo not one but two different derivatives. So there's a hint here which says find f, that's the question, and the antiderivative of f double prime is f prime, and the antiderivative of f prime is f. You're also given two ordered pairs. For the function, an input of 8 produces an output of 2, and for the first derivative, an input of 8 produces 5/8. So I'll give you a second to try and figure out how to tackle this, and then I'll reveal the answer. Okay, here we go. If you take the antiderivative of y double prime, which is the same thing as f double prime, you get this statement here. If you use the first derivative statement, input 8, output 5/8, input 8, output 5/8, you can find the constant for the first derivative, which is 1, and then you have a first derivative statement. So this is just a differential equation. How do we solve that? Same process. Take the antiderivative of y prime, you'll get y. Take the antiderivative of the right side, don't forget about your plus c. Substitute in the point for the function, input 8, output 2. Solve for c. There's your function there. Okay, so for the final example, we're back to velocities and positions. So a ball is thrown up with an initial velocity of 96 feet per second. Initial means time is 0. So in my velocity function, if I plug in 0 time, I'm going to get positive 96. Okay, I'm assuming that the ball is being thrown upward, so I'm going to make that positive. The initial height is 112 feet, so again, time 0. Its position is at a positive 112, and I'm asked to find the position function, s of t, and also the time when the ball hits the ground. So the ball is going to hit the ground, meaning its position is going to be 0, and I need to find that time. One thing they don't tell you, and you need to look at maybe example 8 for more help, is that you're to assume that gravity pulls downward negative at 32 feet per second squared. So this is going to be our starting point. If we have an acceleration, we have s double prime. So I've summarized the numbers here. The antiderivative of s double prime is a velocity. So if I take the antiderivative of negative 32 dt, I'll wind up with negative 32t plus c. So that's our velocity function. I know that when time was 0, the velocity was 96. So the constant is 96. We have a velocity function. Okay. The velocity is the same thing as the first derivative of the position function. So if I undo that derivative, take the antiderivative of the first derivative, I'm going to wind up with a position function, antiderivative. Don't forget the plus c. I know that the starting point when time was 0 was 112 feet. So I plug in 112 for the position, 0 for time, get c as 112. There's my position function. Negative 16t squared plus 96t plus 112. If you've taken physics, all three of these numbers should look familiar. This is a very common quadratic formula, quadratic pattern for the flight of a ball. Anyway, to get when the ball is on the ground, you're going to plug in 0 for the position. Solve this quadratic, you get 2 times t equals 7 and t equals 1. That kind of makes sense, because if you draw the parabola that starts at 112 and lands on the ground at 7 seconds, and then extend the parabola backwards, there's going to be another time at negative 1 when the ball was on the ground. That probably doesn't make much sense because the ball started at a time t equals 0, but mathematically those two solutions do make sense. Okay, so we found the two answers, the position function and the time when the ball hits the ground.